April 15, 1912. As the Titanic disappeared into the abyss of the Atlantic, a legend was born. Among the debris, witnesses claimed to see wooden trunks floating peacefully on the waves like lifeboats. These weren't just any boxes. They were Louis Vuitton trunks. The myth of their absolute buoyancy became the ultimate intrigue of the luxury world. Was it a miracle, or was it pure physics? To understand how a heavy, luggage-filled chest could defy the weight of the ocean, we have to look at the architecture of the seal. Louis didn't just build luggage. He built a pressurized, airtight chamber. The air trapped inside the solid poplar frame created enough displacement to keep the weight of a man afloat. This was the first time the world realized that luxury could mean survival. From saving lives, we move to a much darker modern reality. Every year, Louis Vuitton reportedly does something that defies normal economic logic, destroying its own products. The brand has no outlet stores and zero discount sales. If a seasonal collection doesn't sell, the excess bags are not put on clearance. They are incinerated or shredded. To an outsider, burning millions of dollars of perfectly crafted leather and canvas seems like absolute madness. But in the physics of high luxury, this is a mandatory law of preservation. Value is not determined by the cost of materials, but by absolute scarcity. If Louis Vuitton put their bags on sale, they would flood the market, and the perceived value of every bag in existence would instantly crash. By physically removing excess supply from the earth, they create an artificial vacuum in the market. They aren't burning bags. They are burning the very possibility of devaluation. This creates an economic anomaly known as the Veblen effect. Unlike normal goods, where a higher price means fewer people buy it, for Veblen goods, a higher price actually increases demand because it signals extreme status. This ruthless control over physics and economics guarantees that an LV bag bought 10 years ago holds its value today. But to understand how this empire of untouchable luxury was built, we must travel back to 1854 and look inside the DNA of a simple wooden box. Before the 1850s, travel was mostly done by horse-drawn carriages in the open air. Because of this, traditional trunks were built with domed, curved roofs. The physics were simple. A curved roof allowed rain to shed easily, protecting the contents from water damage. But the Industrial Revolution was about to change the rules of transit. The world moved from horse carriages to steam trains and massive ocean liners. Space inside these new metal beasts was extremely limited and highly expensive. The domed trunk, once a brilliant solution for rain, became a geometric nightmare. Because of the curved tops, it was physically impossible to stack them. They wasted precious cargo volume and created an unstable, constantly shifting center of gravity. Beyond the geometry of space, there was the problem of kinetic violence. Early steam trains shook violently. Ocean liners were tossed by massive waves. Luggage wasn't carefully carried. It was dropped, crushed, and tossed into deep cargo holds. Traditional luggage was made of thick animal leather wrapped around soft wood. While leather looks luxurious under constant kinetic impact and crushing weight, it deforms, stretches, and eventually tears. The elite class of Paris needed a container that could survive the brutal mechanical forces of the new industrial age. They didn't need a bag maker. They needed a structural engineer. Enter Louis Vuitton, a 33-year-old trunk packer. In 1858, Louis Vuitton introduced a radical paradigm shift: the flat-top trunk. By removing the dome, he created a perfect rectangular prism. This wasn't just an aesthetic choice, it was mathematical perfection. Flat tops meant trunks could be perfectly stacked from floor to ceiling inside a train car or ship's hold. But the real genius was in the physics of vertical load distribution. Because the top was flat, the weight of the trunks resting above pushed straight down through the rigid vertical corners of the trunk below, transferring the kinetic energy directly to the floor without crushing the fragile center. Louis didn't just redesign a box. He applied the principles of architectural load-bearing walls to a piece of luggage. To survive the violence of 19th century transit, a trunk couldn't be rigid. A rigid structure snaps under impact. It needed elasticity. Louis returned to his secret weapon: poplar wood. Poplar is unique because it combines low density with high flexibility. Its cellular structure allows it to absorb and dissipate kinetic energy. While heavy oak would crack, a frame made of poplar could slightly bend and flex under pressure, acting like a primitive suspension system for the contents inside. Every joint was precisely engineered, not just to hold, but to transfer forces smoothly throughout the entire skeleton. But the frame alone was weak. The strength came from the covering. Louis moved away from leather, which stretches over time, and adopted a specialized waterproof canvas. This material was applied under extreme tension, creating a pre-stressed engineering system. The canvas didn't just cover the wood, it acted as a structural exoskeleton. When the canvas was glued and tacked down, it held the entire wooden skeleton under constant compression. This binding tension massively increased the overall tensile strength of the structure, allowing a lightweight box to support hundreds of kilograms without deforming. In physics, a corner is a point of maximum vulnerability. Any impact is concentrated into a tiny area, creating massive structural stress. To solve this, Louis added the final layer of engineering: polished brass armor. He covered every corner, edge, and handle base with rigid metal. The physics are brilliant. A brass corner piece acts as a force deflector and distributor. Upon impact, the rigid brass instantly takes the shock and spreads the concentrated force along the edges of the poplar frame. Furthermore, the small brass rivets that held the metal in place did not just hold the corner. They transmitted the energy safely through the frame, preventing point failure. This was kinetic armor disguised as luxury trim. For centuries, leather was the ultimate symbol of luxury luggage. But from an engineering standpoint, leather has a fatal flaw. It is organic and porous. Natural skin absorbs water, oils, and dirt. In the damp, salty maritime environments of 19th century steamships, leather would absorb moisture, become incredibly heavy, and eventually begin to rot. Furthermore, leather stretches unevenly over time, compromising the tight structural tension needed to keep a wooden frame secure. Louis Vuitton realized that relying on biology was a mistake. To build an indestructible container, he needed a material born from chemistry. The solution was a revolutionary composite material, simply known today as the LV canvas. The foundation is a tightly woven cotton grid. Cotton provides immense tensile strength and flexibility, preventing the material from tearing. However, raw cotton acts like a sponge. To solve this, the cotton matrix is coated and fused with a proprietary layer of resins and, in modern times, PVC derivatives. This creates a chemical marriage where the cotton provides the unbreakable structural skeleton, and the polymer coating provides an impenetrable shield. It was essentially an early form of plastic armor, decades ahead of its time. The physics of this coated canvas are staggering. First, it is completely hydrophobic. Water molecules cannot bond with the polymer surface, causing them to instantly bead up and roll off. Second, the coating drastically lowers the coefficient of friction. When the trunk scrapes against a rough surface, it slides rather than tears. Finally, unlike organic skin, the chemical polymer is highly resistant to ultraviolet radiation and oxidation. It does not age, it does not stretch, and it does not rot. This is the true secret behind the Louis Vuitton price tag. You are not buying leather. You are buying a masterpiece of materials science designed to freeze time. Traveling with wealth in the late 19th century was incredibly dangerous. Luggage theft on trains and ocean liners was a global epidemic. At the time, most luggage used simple warded locks. These relied on a single internal metal obstacle, meaning any thief with a basic skeleton key could bypass the mechanism and open a trunk in seconds. A Louis Vuitton trunk was a fortress against kinetic energy and water, but it was completely vulnerable to human intelligence. To solve this, Louis's son, Georges Vuitton, realized they needed to invent a lock that didn't just close the trunk, but actively defended it. In 1886, Georges Vuitton revolutionized luggage security by creating the unpickable tumbler lock. Instead of a single obstacle, this mechanism used a complex system of 5 spring-loaded tumblers. The physics of this lock are based on mathematical probability and extreme mechanical precision. To turn the cylinder, every single one of the 5 solid brass tumblers must be pushed to a very specific, microscopic depth simultaneously. If even one tumbler is a millimeter off, the cylinder remains frozen. This exponential combination of pin depths created millions of possible geometric variations. But Georges went a step further into mathematical convenience. He patented a master key system where a single client could have one unique key that perfectly matched the specific tumbler geometry of all their personal trunks. Each lock was engraved with a unique serial number, and its exact mechanical configuration was registered in the Louis Vuitton archives. It was a 19th century mechanical database. The trunk had officially transformed from a simple wooden box into a personalized, highly secure mobile bank vault. The mechanism was so perfect, and George was so confident in its physics, that it set the stage for the ultimate public challenge. Georges Vuitton was so absolutely confident in the mechanical perfection of his 5-tumbler lock that he decided to put it to the ultimate test. In 1905, he published an open letter in a Parisian newspaper. He publicly challenged Harry Houdini, the world's greatest escape artist, to be locked inside a Louis Vuitton trunk. Houdini was legendary for escaping from handcuffs, straitjackets, and heavily modified bank safes. Georges challenged him to try and escape from a commercially available travel trunk. It was a brilliant, highly dangerous marketing stunt. If Houdini escaped, the brand's reputation for security would be destroyed in seconds. But George knew the physics were heavily stacked against the magician. Houdini's escapes usually relied on exploiting mechanical weaknesses, cheap hinges, loose rivets, or basic locks that could be manipulated from the inside with a swallowed lockpick. The LV trunk had none of these. Its solid poplar skeleton and brass armor meant it couldn't be kicked open from the inside. The complex 5-tumbler lock mechanism was physically impossible to manipulate without the exact key. And most terrifyingly, there was the physics of the hermetic seal. Because the trunk was watertight, it was also airtight. Houdini would have only minutes of oxygen before suffocating. It was a death trap. Houdini, a master of calculating risk and understanding mechanics, analyzed the proposition. He knew the difference between a theatrical prop and a genuine piece of defensive engineering. Houdini never accepted the challenge. He didn't even reply. The silence of the world's greatest illusionist was the loudest marketing victory in history. Without a single performance, Louis Vuitton proved to the world that their engineering could not be beaten by human hands. The lock had defeated the legend. Louis Vuitton is the most counterfeited brand on the planet. But you don't need a fashion expert to spot a fake. You only need to understand chemistry. Look at the handles. Authentic LV bags use untreated, natural cowhide called vachetta. Because it has no synthetic coating, it is biologically active. Over time, it absorbs moisture, oils from human skin, and reacts to ultraviolet light. This triggers a chemical process of oxidation, slowly changing the leather from pale beige to a rich, dark honey color known as a patina. Fake bags often use cheap, synthetic plastics or heavily coated leathers that are chemically dead. They will stay perfectly pale forever or eventually peel off. Real luxury ages. Plastic just degrades. The famous LV patterns weren't just created for style. They were actually the world's first optical anti-piracy codes. In the late 1800s, competitors were already painting fake stripes on cheap trunks. To stop this, Georges Vuitton designed the damier checkerboard and later the iconic monogram. He deliberately made the geometric intersection of the L, the V, and the Japanese-inspired floral motifs incredibly complex to print. In an era before digital printing, achieving this level of microscopic precision with multiple colors on a textured canvas was financially impossible for counterfeiters. The pattern itself was a physical firewall against mass-produced fakes. The final test is pure geometry. Louis Vuitton cuts their canvas with algorithmic precision. On an authentic bag, the pattern is perfectly symmetrical from left to right. More importantly, look at the edges. The brand has a strict engineering rule. The central LV logo should almost never be awkwardly chopped off by a seam. The bag is built around the pattern, not the other way around. Counterfeiters print the canvas in massive, continuous rolls and punch out the shapes randomly to save money, resulting in decapitated logos and asymmetrical chaos. In the world of true luxury, math never lies. If you want to understand true structural integrity, you must look at the microscopic level. The stitch. Modern mass production relies on the sewing machine, which creates what is called a lock stitch. In this system, a top thread and a bottom thread simply loop around each other inside the hole. From a physics standpoint, this creates a catastrophic weakness. Because the threads are codependent, if a machine stitch breaks in just one place, the entire seam will quickly unravel like a zipper. It is a chain reaction of mechanical failure. When you are carrying a bag loaded with heavy items, a single severed thread shouldn't mean the handle snaps off. To prevent this, the most critical stress points on authentic Louis Vuitton bags are assembled using a technique invented for horseback riding: the saddle stitch. This requires a human craftsman using two independent needles on a single piece of thread. The needles pass through the exact same hole from opposite directions, creating a figure-8 pattern. The physics here provide absolute structural redundancy. Each stitch acts as a standalone knot. If you take a knife and slice through a saddle stitch, the thread will not unravel. The opposing thread will continue to hold the leather together with full force. It is an independent suspension system for every millimeter of the seam. But the geometry of the thread is only half the equation. The other half is chemistry. Before stitching, the thick linen threads are heavily coated in natural beeswax. This serves two vital physical functions. First, the wax acts as a lubricant during the intense friction of hand sewing, allowing the thick thread to pass through tight leather holes without tearing. Second, once the stitch is pulled tight, the wax cools and solidifies. It physically seals the puncture hole, creating a waterproof barrier against moisture that would otherwise rot the thread. The wax also drastically increases the holding friction inside the leather, permanently locking the knot in place. It is a masterpiece of microengineering. Louis Vuitton doesn't just rely on history. They rely on modern destructive testing. Inside their secret laboratories, prototypes undergo extreme kinetic torture. Robotic arms load bags with heavy weights, lift them, and violently drop them repeatedly for days to simulate a decade of severe wear and tear. This is a brutal test of physics. It calculates the maximum tensile strength of the canvas and forces extreme shear stress onto the leather handle mounts to ensure they will never snap under the pull of gravity. The physics of luxury must survive anywhere. From the scorching deserts of Dubai to the freezing winters of Aspen, bags are locked in climate chambers and pushed to their thermodynamic limits. They are subjected to intense ultraviolet radiation to test color fade, and then rapidly cycled between extreme heat and freezing temperatures. This thermodynamic testing ensures that the PVC canvas coating doesn't melt, crack, or delaminate. The proprietary adhesives used in the seams must maintain their molecular bond regardless of the environment's thermal expansion or contraction. Finally, there is the physics of friction and mechanical repetition. A dedicated robotic machine opens and closes the brass zippers exactly 5,000 times to ensure the teeth never snag and the metal doesn't grind down into dust. The brass hardware is bombarded with aggressive salt sprays to test the anti-corrosion properties of the metal alloys. Only when a prototype survives this relentless physical and chemical assault is it allowed to go into production. It is a brutal, scientific gauntlet hidden entirely behind elegant boutique storefronts. The heavy brass armor of the 19th century was perfect for steam trains, but the physics of modern aviation demanded a radical change. Absolute strength with zero excess mass. For their modern hard-sided luggage, like the Horizon series, Louis Vuitton turned to aerospace engineering. The heavy wooden frame was replaced by an ultra-thin, flexible polycarbonate composite mesh. The brass was replaced by aerospace-grade titanium alloys. Titanium offers a strength-to-weight ratio that makes it incredibly light, yet capable of absorbing the extreme kinetic shock of modern airport baggage handling without shattering. But as counterfeiters learned to copy geometric patterns, physical security was no longer enough. Louis Vuitton had to move the battleground into the electromagnetic spectrum. Today, authentic LV bags no longer have physical date codes stamped into the leather. Instead, they have an invisible, passive RFID microchip embedded directly into the canvas. The physics of passive RFID are fascinating. The chip has no battery. It remains completely dormant until a specific scanner emits a radio wave. The chip physically harvests the energy from that incoming electromagnetic wave, powers itself up for a microsecond, and transmits a highly encrypted digital signature back to the receiver. This radio signal connects to something even more unbreakable: a decentralized blockchain. Louis Vuitton spearheaded the creation of the Aura blockchain consortium. When a bag is scanned, its unique encrypted code matches an immutable digital ledger that records its exact origin, materials, and point of sale. Mathematics guarantees that this digital history cannot be altered or faked. So it is the ultimate high-tech evolution of Georges Vuitton's original paper registry from 1886. The brand has essentially turned a physical piece of canvas into an unhackable cryptographic asset. Today, the world looks at Louis Vuitton and sees only high fashion, celebrity endorsements, and staggering price tags. But this is the greatest illusion the brand has ever pulled off. Underneath the glamorous exterior of every authentic bag lies a foundation of brutal, uncompromising mechanics. The brand is not fundamentally built on aesthetics. It is a structural engineering company disguised as a fashion house. The true value of Louis Vuitton is not in the logo, but in the century-and-a-half-old obsession with defeating gravity, kinetic energy, water, and time. Trends die. Fashion is seasonal, but the laws of physics are eternal. The structural redundancy of a saddle stitch will always hold. The cellular displacement of poplar wood will always float, and the chemical hydrophobia of a PVC-coated cotton matrix will always repel water. Louis Vuitton created a product that actively resists entropy. While everything else decays, their canvas remains frozen in time. They didn't just design luggage. They engineered an artifact meant to outlive its owner. The story of Louis Vuitton is the ultimate proof that true luxury is born from solving impossible problems. It is the story of how a simple 33-year-old packer and carpenter looked at a chaotic, violent, industrial world and decided to bring it to order through geometry and mechanics. He protected the fragile lives of the elite inside unbreakable wooden walls. Today, a Louis Vuitton bag is a status symbol, yes, but fundamentally, it is the absolute mastery of material science. It is the ultimate container. Thank you for watching. If you appreciate the pure engineering and physics hidden behind the world's most famous brands, please hit the like button and subscribe to Simply Explained Pro. Let us know in the comments, which brand's mechanics should we deconstruct next? Your support is the engine that keeps this channel running.